Good morning, class, and welcome to round two of trying to figure out what sort of things we can put into our review project. So, last time we looked at Newton's first law and some of the examples that we could have with that. This time we're going to look at some applications, and today let's look at making problems for applied and named forces and the normal forces of problems. So for this application example, we're going to look at applied forces. One problem must have three different applied forces on an object. That's one of the conditions that you have to fulfill for one of your problems. So to do this, well, if you're having trouble getting started, I recommend what you do is you start by just drawing yourself a little box. And then think of this, think of the condition. I have to have at least three different applied forces. Well, I should draw three different arrows and give them all different names. I'll call this force A for force applied. Maybe the other one's going to go this way for force B. And I'm going to need a third arrow. I don't know which direction it'll go. Well, I can make it any direction. I recommend that you have it go either left or right, or rather in the same plane of direction of the other two, because we haven't done two-dimensional motion yet, and if I had it moving up, that would complicate things. That's something that we would approach in Physics 12. But this isn't a situation, this is just a box with arrows on it. How do I turn this into an example? How do I turn this into a problem? What you have to do is use a little imagination. You have to make a story for this. I can imagine that force A is applied by Alfred, because A is Alfred, and force B is applied by Barry, and force C is applied by Chuck. So now I've turned these three forces into names. There's Alfred, Barry, and Chuck. Okay, Alfred's pulling one way and Barry and Chuck are pulling the other way. So they're fighting over this object. There we go. I've just made some imagination. Now I can go ahead and I can expand upon that. Let's go ahead and begin writing this out. Cocoa Puffs, for those who don't know, are a breakfast cereal. So now that I've established the situation, all I need to do is I need to provide some values. There we go. These values, they were just things that I just randomly thought up. 12, 7, 10. I have information here, but I don't have a question yet. What do I need to find? Maybe I want to know where the Cocoa Puffs go. That might be reasonable. But since we're talking about forces, we always talked about the direction of motion and the motion being part of acceleration. So I will ask for the acceleration. And now you're like, awesome, my question is complete. This makes a ton of sense. Well, okay, this situation is entirely made up and it doesn't make much sense, but the idea here is that this might be something that's solvable. What you should do before you consider handing it in is completing your answer key. Thankfully, because it's absolutely necessary. But if you were to do that, and you're thinking about, okay, I'm going to make my answer key here. I'm going to need to use the net force. I know Barry and Chuck are working in the same direction, so I'm going to add those forces. I'm going to subtract Alfred force. That seems good. Do I know this is a number? Check. Do I know this is a number? Check. Do I know this is a number? Check. Okay, I got all of those. And I'm trying to find acceleration. So if I was looking at mass times acceleration, the acceleration is my question mark. That's fine. Uh-oh. Do I have my mass? Not yet. Oh, good thing that we tried to solve it, because we know we made a little mistake. We didn't include our mass. So let's go ahead and fix that. I'll just erase that. There we go. Bam! This is now a solvable problem because I have force Barry, force Chuck, force Alfred, and I have the mass now. I have all of the pieces that I need to find my question mark. How do we make a problem for our applied force? Start with a box, look at your condition, and just throw meaningless arrows on them that match it. Then with a little imagination, just add names to them and make up a situation which may exist. And make sure to double check that you have all of the necessary information. You should end up solving for one particular value, be it acceleration, be it mass, be it maybe one of the unknown forces. As I could have given the acceleration and maybe left Chuck's force as the unknown. There are so many options that we could do when making force problems. Let's look at normal force. All right, normal forces. One problem must demonstrate a normal force that is not equal in size to the force of gravity. How do I make a problem for this? Start with your box again. Now, this one I have to consider, what can I do to make sure that my normal force isn't equal to the size of gravity? Well, if I added in gravity here, this means I can do a few things. I'm actually going to draw a few boxes to demonstrate. All of them are going to have a force of gravity. And I need to make sure my normal force is not the same size. So if I just had this box sitting on the ground and it wasn't going anywhere, the normal force would actually balance that. And that's no good. This is a bad situation because it doesn't match our condition. But one of the ways that you might remember is, what if you had an object being pushed into the wall by some applied force? Remember, the normal force is always perpendicular out of the surface. In other words, it'd be this way. In this case, the normal force actually relates to the applied force. These are connected. Therefore, it has nothing to do with the force of gravity. This is going to be an acceptable type of problem. Alternately, what if you really want to have that object sitting on the ground? How can I make sure that my normal force doesn't equal it? Well, remember, the normal force is exactly as much as it needs to stop from breaking through the ground. So if you pushed down on the box harder with, say, an applied force, the normal force is actually going to have to be a whole lot bigger, because it's going to have to be as big as the applied force plus the gravity to end up equaling enough force to keep it from breaking through the floor. This would be another way that we can make a situation with normal force that would be larger than the force of gravity. You could flip the applied force the other way to make the normal force smaller. Either way, we can see that there are many things that we can do to make sure that our normal force is not equal to the size of gravity, and we can make a problem that matches this condition. I hope those two examples were helpful. I'm going to give some more examples tomorrow with the other types of forces. Have a good day.